Okay, our next speaker is Mario, I0NAA, and Mario has been a licensed radio amateur since 1970, back when tuning meant knobs and not menus. His lifelong focus has been on weak signal work and radio astronomy, where patience is mandatory and noise is part of the fun. Today he's active on EME and experimental radio astronomy, and in 2015 he installed a 5-meter dish and has been listening to the universe, mainly chasing faint cosmic signals such as pulsars and trying to squeeze the last fraction of a dB out of a system, just like the EME guys. So he developed 3 software tools such as Murmur, Total Power, and Presto, Best Profile Analyzer, widely used in the amateur community and occasionally finding their way into professional circuits. So please welcome Mario.
How do you say? Buenos dias, queridos amigos. Buongiorno, good morning. And guten Tag, Rainer. Thank you for organizing all this in this paradise. Today I'm going to talk about something new, I would say, for our community, a new method to evaluate our system, to evaluate the sensitivity of our system, using, of course, the noise, but through a new parameter that is very, very well known in professional radio astronomy. This parameter is called SEFD, System Equivalent Flux Density. I know that there are some professionals here on radio astronomy, and I hope that this guy will shut up, because otherwise, I don't, but it's over there. So I think that you will be very patient with me. So I have some equation there. I promise to keep at the very minimum, but just interrupt me if I slip too much into the sleeping pills territory. So let's start. I think that we all know the two key things of our hobby that are signal and noise. And of course we know very well the signal to noise ratio, that is how good we are to extract a signal from the noise. And we used to say that we are so good that we are able to extract the signal below the noise. Many times we say, we are able to detect signal below the noise level. But is this totally correct? Well, yes and no. Because the right sentence, and I will elaborate a little bit more during my presentation, is that we should say the signal is below the noise only on short time scale over very wide bandwidths. What we do actually, we apply coherent or folded integration, and then we are able to extract. So yes, the statement is true, but we should say a little bit more if we talk to professional guys. Among us, we can say whatever we want. And this is something that is a key factor in radio astronomy, of course. I'm pretty active in EME, but most of the time I'm trying to catch the noise from the cosmic radio sources. What is noise? Noise is anything unwanted that disturb the signal that we are interested in. And the signal can be also noise. In the case of radio astronomy, the signal is noise. Noise is internal to our system or external, like artificial noise, terrible these days. I started in 2 meters, then I tried 70 centimeters, but in my area it's totally impossible. So I had to migrate in 23 centimeters, and now I'm there. I will talk about, sorry about that. I will talk about thermal noise, because we have seen our friends discussing about the temperature, how the temperature is related to the power of noise, and we discuss, of course, also about cosmic noise, that is our reference for our measurements. Thermal noise comes from the simple setup. If you heat up a resistor, the electrons inside start some Brownian random movement and generate some current that we can measure, and is represented from this equation, where there is the famous Boltzmann constant, the temperature, and the value of the resistor. This thing can be this simple setup can be actually designed extracting a pure resistor and a theoretical generator. I don't want to go into the details of the equation. However, the things that you can see that at the end the power that the resistor here can generate is expressed from this formula. And this is interesting because in this formula, on one side we have power, and the other side we have temperature. So that means that we can use temperature, the so-called equivalent noise temperature, to quantify the power of noise. This is the simple equation that relates the two things. I've seen sometime somebody that saying, my antenna were so cool that are frozen this morning. This is true, this is true. I've seen this thing. Well, the relation is there, but it's not actually the reality, this thing. So, usually in ham radio we use decibel. In radio astronomy we tend to use temperature because the signal are so low that decibel, that as a logarithmic thing, are not adequate to describe the thing. How do we measure the performance of our system? We know very well, P hot, P cold. We point the antennas to a hot source, and then we point to another place that is the so-called cold source. I will discuss a little bit because this is quite a sensitive measurement, so we need to keep some rule in order to avoid mistakes. This relationship here can be translated when we go to our system into this other relation here with the logarithmic, and this is expressed in decibel then, and we have the equivalent temperature. And now we start talking about temperature. Equivalent temperature of the system, equivalent temperature of the antenna, and equivalent temperature of the so-called reference sources. The reference sources, the equivalent temperature of reference sources usually is very, very low compared to the equivalent temperature of our system, at least one order of magnitude. So we tend to simplify this equation into this other here, and taking in consideration the equivalent temperature of the antenna can be expressed by this formula here. You see here is a strange number. It's not a magic number, but on the other side we have Boltzmann constant and flux. Flux is a measurement of the noise that one source is sending. In radio astronomy, this is expressed in Jansky. That is something 10 to the minus 26, so a very, very small quantity. Boltzmann is 10 to the minus 23. The relationship gives us this number. So this equation tells you that if we know the flux, so how much noise a cosmic source is sending, we can calculate the antenna temperature, calculating the effective area of the antenna. And this is the tricky things, because the effective area of the antenna got a parameter that I'm using 50 or 55, but it's really tricky. So we need to put a lot of parameters to make the assumption, to make the calculation. So we need to put antenna efficiency, system temperature, and then we can calculate these things. Of course, we want to make this measurement as accurate as possible, so we go usually and we measure the sun. But how can we make the equivalent temperature of the antenna? Of course, there are many possibilities. The things that I'm going to show you, how to use my program that is Total Power, that is downloadable for free from my website. This program is connected to, in my case, is connected on one side to the so-called RTL SDR, that is the small dongle that was costing $20 before the COVID. Now it's maybe $45, $50, but still very, very cheap. And on the other side, Total Power interface with the PST rotator. I think that most of us are using this outstanding program from Codrut. And the PST rotator can handle basically any mechanical rotator on the market. So Total Power on one side control the antenna, on the other side get the signal from the antenna and elaborate a little bit. So can actually do the measurement as I will show you. What is the dongle? Dongle is an SDR, very, very basic SDR, 8-bit, actually 7+1, because 1 bit is used for the sign. It's very wide range between 24 and 1.7 gigahertz. And sampling rate is 3.2 up to 3.2 million samples per second. That is equivalent to 3.2 megahertz of bandwidth. And we are not violating Nyquist because actually Nyquist is saying that if you sample at the same frequency, you should have half of bandwidth. But in this case, like in all the SDR, whenever we sample, we have two data, I and Q. So the sample rate is equivalent to the bandwidth. But this dongle that is very, very cheap, I got a lot of limitation. I just listed few here, intermodulation, aliasing, overload. But for us, the most critical thing is the performance instability caused by thermal drift. So when you attach this thing starts to navigate, the noise is moving and so on. Two solutions here. This is what I'm doing in my station. Actually, I acquired here an heat sink dissipator from Etsy. Etsy is something like Amazon for poor people, something like that. But you find very interesting things, even cheaper than eBay. It's kind of aluminum things like a glove. You insert the key, you connect the fan to the USB, and this thing stabilizes the temperature. So without the heat sink, before stabilizing, I need to wait maybe 1.5 hours. With the heat sink, I can stabilize up in 20 minutes. This is very useful. This is one solution. The other solution comes from Victor, U-A9FAD. I think that most of us knows this guy because he's very, very active on the band. Very good signal. He actually put the RTL SDR into an aluminum box. He put a heat sink with a regulator and everything inside the thermal-insulated enclosure. And the stability that he achieved is very, very good, you see? So, to some extent, this $20, $30 that we invest in this thing are worthwhile, because with some trick you can have a pretty stable system of measurement. How do you measure the antenna temperature? Actually, how you measure the Y factor? You point the antenna to the sun, then we will see how to, Carsten already showed us how to predict the sun noise. Of course, I have another thing to predict the sun noise, but I think that it's exactly like Carsten showed us. This is the main screen of the of the total power. So when you point to the sun, you reset things, and then you move your antenna away. Automatically, you see both on an analog meter and on the main screen the value of the dB, how the noise is going down. One recommendation here, to measure the sun noise or the noise of any other object, you should not measure the object and then go to Lee or whatever is it. The correct technology is to measure the sun noise and then to move maybe, in my case, I move 15 degrees from the main target away. That in my case is about 5 times HPBW. My antenna got about 3 dB, 3.2 dB of HPBW, so I move away about 15 degrees, and then I read here the noise, the Y factor automatically. So very easy to see. Actually, it's a matter of a few seconds basically. Total power. 2 words about total power. On top of this, you can make many other things. One of the most popular things these days, actually, for the people that is going outside, rovers and so on, is the possibility to hear the noise. I have an audio tone that the audio tone change with the strength of the signal. So even if you are outside, and usually when you are outside, the sun actually makes the reading of your laptop very difficult. You can just listen to the tone, and you say, "Ee," And it's very easy to point the antenna. Very useful function. Of course, if you are at home, not much of interest, but if you go around, it's very useful. I have a real-time mode, so you can see what is on the band. I have a peak holder mode in which you can, this for example is the ADS-B beacon of the aircraft. You can see whatever you want. So if you have a peak in real time, you don't see anything. But of course, in the peak mode, you can see everything. I have also a kind of folding mode that make very easy to detect the H-line of our galaxy. And then I have something similar Carsten show us, that is the 3D mapping of the object, and I will show a little bit better later on. I have a cosmic map, so you go with the mouse, you point anything that you want to see, you click, the antenna moves there, and then you see immediately how the noise is moving. And last but not least, I have what I call noise horizon mode, very similar to what Carsten showed us, but with much more detail, because my system is basically for radio astronomy. For radio astronomy, you need to see exactly, not the block, but you need to see exactly what is the noise, the background noise that you have. I was telling you that yes, we need to see the things that you usually look at to make the Y factor measurement is the sun. The sun, of course, is very, very variable, very, very variable. Maybe 6 months ago, maybe a little bit more, got very, very high activity. Now it's down to normal activity. So we need to predict the sun noise in a good way. In my case, between active sun and quiet sun, I have more than 2 dB of difference. So make a lot of difference. Of course, the bigger antenna, the bigger is the difference that you can see. How can you predict the sun noise? With the program Murmur, of course, with other program. Of course, the reference is the programs of Doug, of course. This is a kind of kernel of what Doug did. You just on Murmur, that is my other program, you just put your parameters. You need to put the EME amplifier gain and amplifier noise figure and blah, blah, blah. The program calculated the equivalent noise temperature of the system. And then you go to this screen here, and this screen here interface directly with the NOAA Solar Observatory, download the data, calculate the best set of parameters, and make a spline cubic interpolation of the data of NOAA's observatories, and gives you the sun noise factor that you should expect. Unfortunately, this NOAA Solar Observatory network these days is not working very well, and a lot of time you can see -1 means that data were not cached, were not communicated or whatever. So I just put the possibility to look at to the data of the day before. This is, of course, is not correct because the sun can have, big deltas in a few hours, but still there's some reference point. So at this point, we know exactly what is the Y factor noise that we should expect. Murmur gives to you not only how much is the sun noise that you can expect, but also gives you the noise that you can expect from the major cosmic sources like Cassiopeia, Cygnus A, Taurus A, Sagittarius, Virgo, and Moon. I also put here a quasar that is 3C 273, but this is a dream. I think that I detected this, but I'm not really sure that. So, because with my system, I have a 5-meter dish, I should have 0.02 dB of noise. That is to be sure that I detected this. Before saying this, I want to have a double check. So, interesting, the moon noise. The moon noise is also a variable. The others are fixed. Actually, I calculated the noise, the expected noise with a linear interpolation, while with the sun I'm using a cubic spline interpolation because of the shape. The moon is variable with illumination. So why the moon is emitting noise? Because it's warm. And what I did, I calculate the lunar phase, I adjust the lunar phase with a lag of 3 days, and then I calculate the surface temperature, and then I calculate the noise that we should expect. And it's pretty accurate, I need to say. So you have the reference of the sun, and you have the reference of all of this. Of course, depending on your antenna, to receive all of those, except receive 273, maybe somebody can also, is much bigger than my dish can receive. You can use any of those sources. 2 words about Murmur. Murmur was born as a program to predict the possibility to detect pulsars. So you just put all your station parameters here. The system calculates system equivalent temperature, and here at least the pulsar that you can detect. But today I'm not going to annoy you with pulsars. I will just focus on the M radio part of this program. There is one possibility that I call system mode, system mode, in which you can have something very similar to the things that Carsten showed us. He put a much better graphic, I need to say, and this is a stimulus to improve my graphic. Here I have few sliders, a few things, and you can play with it. It's pretty interesting to see, even if you want to show to somebody. It's very interesting to see, because actually just moving the sliders, you see how the equivalent system temperature moves, and you can show to friends how this thing works. Very interesting. Another interesting thing is what I call plane observations. Here, of course, you need to put your location, and the system calculates automatically the visibility of the object, of the cosmic source, and of course of all the pulsars. I have here 3,600 pulsars. But I have also the Sagittarius, all the main cosmic sources, and also I have here in the bottom what I call noise horizon. In my case, for example, from 330 azimuth up to 360, I have the house. So it's totally useless that the system tells me that the moon is visible there, because I cannot receive anything. So you mask the result, and so you can adapt its output here to your environment. And then you have azimuth and elevation for every single object. Very useful to plan the observation. And another, I think, a very interesting thing, that once you measure the sun noise, you just put in the system, you just save, and here you see the history of the sun noise from, in my system, I think from 2018 or 2017, I don't know. Here you see the peak that we had some time ago, and now the sun is descending. And here I record not only the performance of my system, but also the flux of the sun. So pretty useful thing. This program is also downloadable for free from my website. Now I want to show you the 3D function that is pretty interesting to see. It's moving, yes. Yes. No, this one is not moving. No, on the left. The left, I don't see the clock moving. Okay. Now it's moving. Now it's not synchronized. But anyway, the concept on the right side, you see the antenna moving. That was the moon. And the antenna, you see, is making a kind of spiral around the moon. And here, you can see of course you cannot read because it's too narrow. You can see the value of the noise that the system is recording. Look at on the left side, actually, here, you can see the number on the plot. And this thing doesn't tell you much. Tell you that when you off-point the moon, of course, the noise is going down. But look what happens when the antenna is going down, and you see that I have trees there. The antenna goes down, and you will see here that the noise, you can also see on the analog meter here, there is the real time and the other one is filtered with the moving average filter, so it's a little bit smoother. Of course, you can modify all the parameters. And now you will see that as the antenna goes down and look to the trees, the noise is going up, obviously. But the interesting things happen when the antenna finished the mapping, and it was almost finishing. Now here, take the last reading, okay? And now you can stop the recording and then analyze the result. And this is what you were seeing, the noise of the moon together with the noise of the ground. Look how much the ground is influencing the measurement of the noise. Very, very much. And this is valid especially for the weak signal, of course. Yeah, you can also make a counter map and so on. This gives you a better view of the noise. This is again moon, and as you can see, the ground has a big influence when you measure very little. This is why instead of going to the cold area, you should move around the same elevation, especially if the elevation is low, because then the ground noise is not, I mean, it's influencing good measurement, so it's disappearing. But if you have the moon is, I don't know, 40 degrees, and then you have Leo at 20 degrees, then you have the ground influence that is very strong, as you have seen, that is actually making your measurement not too accurate. Let me show also this one that gives you the other input. No? You will see this one. Big carrier. In fact, this coil is called carrier. This is the sun. It's better. Okay, that's fine. Okay, this was the sun. You have seen that I can interpolate the data, so you have very, very good shape. This is again the moon with the influence of the ground. This is Cygnus A. Cygnus A is a fantastic object, 700 million light years away, here where Amoebas. This is interesting. Let me point a little bit on this one. This is what I call noise horizon. And as you can see the trees of my garden here. And also you see that at the center, this kind of smoke. This is the Milky Way. You can see the Milky Way with making this horizon scan. And finally, this is the last one at ES. You can also make a counter plot, and actually you can see very clearly the trees that are in my garden. Very interesting, especially if you want to make some radio astronomy things. That means that you need to be sure to search for your object that is very low in terms of noise, where there are no trees that are obvious, but you know with this map how far you need to be in order to be able to catch. This is of course influence also EME, but not as much as it's influencing radio astronomy measurement. The caveat was the trees. This is another caveat. Be sure that when you make noise horizon, you put the right stop. But this is my half-inch cable that 2 weeks ago, I mean, instead of putting 330 degrees, I put 340, something like that. When I came back and was no signal, everything was stopped, this was the result. This week I'm going to replace. So be careful, two things. One, the noise, and the other one, be careful about the limit of your horizon exploration. So we have seen the classical methodology, we are using this. Now let me introduce this thing. We need to put a lot of parameters if we want to be sure to take the right measurement. When we compare different systems, we need to say, I have a 3 meter antenna, W2IMU feeder, 0.3 dB, blah, blah, blah. So it's not so easy to compare our system from a reception point of view. In radio astronomy, in professional radio astronomy, there is one single parameter that actually put everything together, and it's called system equivalent flux density. What is it? The formula is there. Basically, it's a theoretical number that is the flux density. Flux is how much noise a noise source can emit. The flux density is an hypothetical radio source that produces at the output of radio telescope a signal to noise ratio of unity. So it's hypothetical. So it's something that produces exactly the same result that your system as a global is producing. What is the benefit of this thing? It's easy. When you know the SEFD of your system, the lower is the better. The lower is the SEFD, the better is your system. And SEFD accounts for the combined effect of everything. And two systems with the same SEFD are equivalent. So next time we meet each other, I hope that somebody, I have 2000 SEFD, instead of say I have 10,000 SEFD. It would be very interesting because from the reception point of view, and I will show you the data, is very useful number. Some equation, but I will be very quick on this. Not only this number characterizes entirely your station, but with this number it's possible to predict what is the noise figure, the ratio SNR that you want to see for a specific radio sources, using modifying two parameters that are the bandwidth and the integration time. So again, the signal is below the noise, but what we do, we integrate, so we modify a little bit the background and we are able to detect. So it's a bonus, and you will see how we can use it. On the other hand, the SFD, how you calculate the SFD, forget about I will be pleased to go with you through the equation, but look at this one. The SEFD is equal to the flux of the source that you are observing divided by the Y factor that you derive from that. That's it. You don't need to put the equivalent temperature of the system. That honestly we don't know very well. You don't need to put the fantastic number that is the dish efficiency. I'm using 50, I was using 60, maybe I use 45. You don't need to do that. You have a number that characterizes and it's not forgiving this number. So we cannot play with it using another efficiency of the antenna. This number is not forgiving. This number characterizes entirely your station, the receiving part of course. Very interesting. How do we do that? Mormor got a little button here in the screen. It's called SEFD analysis. If you click on this, you have two different possibilities. The first one is this one. If you know the SEFD of your system and you know the integration time, how much time you want to integrate, how long, and you know what is the bandwidth of your system, and you know the flux density of your sources, you can see what is the expected signal to noise. So in this case, just an example, 1.2, yes, we can receive this 0.02. Maybe I need to increase integration time, but you just play with number and you can plan with it. Very interesting. And of course, the other one, very simple. The equation are very simple, as I show you. Calculation are simple as well. You calculate the Y factor for one source here. You put the source flux density, and magically you have the SEFD of your system. Let me show you the calculation that I have done on my station. I tried first with the sun. The same principle. No, this is the Crab Nebula actually. No. Yes? Yes. This is the Taurus A, the Crab Nebula. I know the flux of the Crab Nebula because you can find on the screen that I showed you before. In this case was 912 Jansky. Not very weak, pretty strong. I think that even with 2-3 meter dish you can detect this. You calculate the Y factor dB level, moving the antenna away, avoiding to move the antenna to a point that is not at the same elevation because otherwise you add variability to this number. You move away, and in this case I measured here 14,200 Jansky. Then I tried with the moon, exactly the same thing. I put the flux that you can calculate, the moon will calculate for you. You put this number here, and then I have 14,000 blah blah blah. I did that the same thing for Cassiopeia, another strong noise sources. On the left you can see how much the total power is showing to you, moving the antenna away. And then here I did that also with the sun, because I mean it is exactly the same thing, but making with many different sources you can understand how close you are. And then what I did, I put everything together. So the theoretical SEFD of my system, the things that I calculated, putting the equivalent noise temperature, the noise figure of the preamplifier and blah blah blah, was 10,406. That was the theoretical SEFD of my system. However, measuring this thing, I have a cluster of objects like Sun, Taurus, and Moon that are very, very close, 1.7%, so pretty affordable, pretty good number, so means the number is consistent. And then I have Cassiopeia that is much, much worse. Remember that the lower the better. So from this I can derive that the SEFD of my system here is about 14,300, you know, right in the middle. So why then, I ask myself, why I mean so much difference? Then that's the interesting part, because actually I try to move parameters on Murmur and calculate again the SFD, and I found obviously, but I like to confirm theoretically the things that are obvious. I found that the influence of the loss before LNA, as Casa was telling us, it's really big. In my system, I put 0.1 dB, maybe was not correct. Just moving to 0.3 dB, I am exactly at the SEFD I was calculating. Very interesting, because we can play this number, and playing with this number, you can come to a kind of action plan. Example, you want to double check the flux assumption of the sources. Are very, very stable. Sagittarius is moving a little bit, you want to see the latest update. Of course, the SDR must be without the AGC, because otherwise the thing is modified. Verify the cold temperature point. When you move the antenna, you need to be sure that you are not pointing a tree, but you can do that making the solar horizon, the noise horizon map. And so what we can do is just a rough thing, but you can you know your station very well, so you want maybe to try different offset of your antenna, always at the same elevation. You want to see maybe the real loss before the LNA. That is not easy, because you need to go up to the feeder and measure there, and so on. The good point is SFD compress everything, including mistakes, in one number, and we are able to compare our station. We are able to elaborate how these things compare to the professional world. I said, oh, I had 14,300. Let me see something professional. I asked Lady ChatGPT to extract from the network the SFD of famous antennas, and then I was really depressed because of this. Look at that. FSBER 15 Jansky, 14,300, so disappointing. SRT, that is Sardinia Radio Telescope, 64 meter, they got 36 Jansky, and blah, blah, blah. Of course, there are professional things and blah, 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 but, you know, among us we can compare, and one thing that you should remember, that this thing is not forgiving. It's not forgiving. Whatever you measure is there. There is something behind that we need to discover. And I hope that this methodology will help all of us to improve our station. What's next? I think that I will incorporate in Olmo the possibility to save the SEFD measurement on top of the noise of the other, so you can compare during the years like I do for the sun. Total power, and I was discussing in Harka also, we incorporate additional SDR platform. I'm quite in a good way, of course. The new hardware come one after the other, not all together. And obviously, in the next meeting, you should expect from me some other astrophysical thing. Why? Because the moon is visible only a few hours a day. What we do for the rest? We invested thousands of dollars on this, so we need to utilize this thing much better. So that's all. Grazie, thank you, and for Rainer, ich habe fertig, for my German-speaking guys, this ich habe fertig, I think that remember to use something that is a totally wrong thing, was Mr. Trapattoni actually was saying. That's all.
A few minutes for questions.
Yeah.
Hi, John G4SWX. Whilst I understand the tradition and the rigour that radio astronomers have put into the way they do source versus quiet sky by keeping the elevation constant, that makes an assumption about the dish that all of the side lobes and spillover is asymmetrical. If you try doing some of this with a Yagi array, as you move, even at the same elevation, your background noise temperature goes crazy, as you probably guessed from the maps from my presentation yesterday. So it's just a caveat. And even with a dish, the supports of the feed cause small perturbations in the side lobes, and that can upset it as much as well.
Absolutely, this is totally true. This methodology is more for dishes, because, and even for dishes you have side lobes.
It works for me as long as you take the map.
And in fact, the things that I suggest is to use the noise horizon function, so you know exactly what is your noise horizon, because you see numbers. Maybe are side lobes, maybe somebody is switching on a jammer of 23 centimeters or whatever. So, but you know, and then you understand if your SEM elevation is valid or not. It's very important. Example, if I have the sun just beside a tree, and then I move and I just point to the tree as the noise horizon map is showing me, and then it's totally wrong, the reading. So yes, you need to be very careful, and of course for Yagi arrays you need to be double check, but I think that it can applicable. I think that can applicable this thing. It's very interesting because with one number you have everything. Really, and we are able then to compare our station without saying 10 meters, 2 meters or whatever.
Oh yes, sorry, Mark, you're right.
Anything else? Yes.
Can you tell us something about the hardware? I don't understand how you get the 3D.
The hardware means what? The hardware is.
Which hardware do you use? Yes.
The hardware for the rotator are the rotator.
Yeah, I don't know.
The rotator of the antenna. The antenna is just to. The antenna is the 5-meter dish that was belonging to Hannes or 5 GFL.
How do you get the data from your router into your program?
Is with RTL SDR. RTL SDR is an SDR that actually on the input get the signal. Of course, I have a preamplifier. Then I go into the SDR. The SDR produce two numbers that are I and Q. I just grab those numbers. All the program is written in C++. Sorry, but Python is not for me.
But azimuth and elevation, where does it come from?
What elevation?
Yeah.
I mean, depending where is the noise source.
PST rotator. From PST rotator.
How do you point? It's a PST rotator. The program, okay, now understand. The program knows where is the source. because the program got embedded the right ascension and the declination of every source that is there. The program knows where it's located, so generate the real-time azimuth and elevation. Every seconds, I generate a new elevation and azimuth. I send these two numbers to PST rotator. PST rotator is the program that controls the rotator, and PST rotator, the program for code root, actually moves the rotator. That's it, and it's very accurate, very accurate. Here it is. This is very accurate because the pointing system, the calculation of azimuth and declination, azimuth and elevation is derived from WSJT program. WSJT program, the things that Joe wrote, actually the code is available. I took the code and it's very precise, and it's been designed from Joe. So, and I just used the routine to calculate azimuth and elevation from there, and I transmit, I think it's with the UDP protocol to PST rotator, and PST rotator takes care to point at the object. It's totally automatic, so you don't need to do anything.
Okay, I use it only if I want to use it, only if a noise meter.
Yeah, I mean, you don't use the noise horizon thing.
What's with the tolerances and the temperature? Especially if you use higher frequencies, you have only for the moon 0.5 dBs or 1 dB. Can you show
the range, this is not calibrated. That's a good question. The system is not calibrated, so to calibrate this, I would need a reference noise sources and calibrate and put the correction inside. However, when we make measurement, we don't really need calibration. We need stability, because we make a comparison between one value and the other. So it's the dynamic range that takes care. This thing can 25, 30 dB of dynamic range, more than that. So.
Okay. Is there another output, for example, for spectral view possible? Then you can see the diagram much better and what happens there.
There is a spectrum analyzer, but it's not so sophisticated. So this is one thing that I cannot. Of course, if you would like to add something to this, just drop me a note. One thing that for sure, the things that I show you are the things that I will add. If there is something else, I will be more than glad to add. Of course, my group is not very big, it's one person only. So you need to be a little bit patient with and everything is written in C++. The Mormon is a simple program, very simple. The total power is something really, because in the total power they are running, I don't know, maybe 10 threads, 10 different programs that are doing whatever, and I had a lot of help from Mick because the things were stopping, I couldn't understand why I was not using properly the thread, so there are a lot of things. Whenever I touch something on the threads, I need very careful. But adding a spectrum viewer would be something possible. Not very difficult. Anyway, the things I'm working with is a package under Windows to detect pulsars, and I hope that everything will be ready by the end of this year. Everything is running in parallel. I have many threads working, but sometimes some thread stops, even on myself. So, and you need to push me.
Thank you very much, Mario.